C-97 aerial delivery. For isolated combat units faced with a lack of supplies, a large-scale delivery of ammunition, small equipment, food, and medicine can mean the difference between victory and defeat. Now, 26,000 pounds can be unloaded in 12 seconds. Developed by Wright Field's Equipment Laboratory in cooperation with Boeing engineers, this new monorail aerial delivery system, as installed in a C-97, is also being adapted to the C-82 and the C-74. Although any type of aerial delivery container may be used, as dropped in these tests from the C-97, standard A6 containers were used, weighing 300 pounds, each with a G1 parachute and fastened into bundles of 5 for the so-called daisy chain launching technique, where 2 static lines from the first container releases the chutes of the 2 following containers, they in turn releasing the chutes of the 2 remaining containers. The sling-type harness is designed to permit both loading and suspension from the trip mechanism of the trolley, which rides on an overhead monorail. The electrically operated loading mechanism has a hoisting capacity of 5,000 pounds, and by means of a clutch, it can traverse the bundles to any desired location along the monorail. As each bundle is positioned, the loops of the sling harness are transferred to a monorail trolley. Each of these 17 trolleys, one for each bundle, are secured to the discharge cable and traversed back by 2 discharge motors at the aft end of the monorail during the drop operation. A tie-down harness secures the load during flight and is automatically released at the start of the discharge operation. A 26,000-pound cargo of urgently needed supplies for aerial delivery. The trip bar above the cargo doors releases the bundles, and the individual containers are on their own. Traveling at 150 miles an hour, the entire load is dropped in 12 seconds. Delivered from an altitude of 1,000 feet, the ground pattern of the entire load is 2,400 feet long and 150 feet wide. This tight pattern makes the collecting of supplies easy. Slow motion analysis of the daisy chain technique reveals the function of static lines from one container to the parachute of the following container, and thus initially linked together in groups of 5. Other tests at lower altitudes point to the possibility of an even tighter ground pattern. Here, but one run was needed over the target to discharge the complete load. Older methods required several passes, which unfortunately presented a recurring target for the enemy. The C-47s, when used in the past for aerial delivery, had a capacity of 5,000 pounds. Here, the C-97, with its 26,000-pound cargo, packaged for daisy chain delivery from a monorail, marks a major development in aerial delivery. Following the early performance records of Lockheed's P-80, propelled by a centrifugal compressor-type jet engine, jet fighter research centered on the development of a fighter of comparable size propelled by a jet engine of the axial flow compressor type. This resulted in the XP-84 Thunderjet, designed and built under the joint supervision of Republic and Air Materiel Command. Compared with the P-80 in size, the XP-84's wingspan is 2 feet less. From nose to tail, it is 2½ feet longer. Its weight of 13,400 pounds is approximately 1,500 pounds heavier than the P-80. One of the most striking differences in outward design is the air scoop located in the nose. The temporary installation here of test equipment during its early flight tests are evidenced by the rakes projecting from the center partition and sides of the air scoop. Through these, test data on pressure distribution and temperature was procured. The pressurized and air-conditioned cabin is equipped with a pilot ejection seat and an electrically operated bubble canopy that can be opened at all air speeds and easily jettisoned prior to an emergency exit. The rear section of the fuselage is quickly removable for a complete engine change in 50 minutes. The General Electric jet engine, designated as the TG-180, accounts for 2,300 pounds of the XP-84's total weight of 13,400 pounds. But the outstanding design characteristic is the longer overall dimension and relatively small diameter, made possible by the axial flow compressors. The Thunderjet is sleek, flush-riveted, polished, and exceptionally clean in design, incorporating the new Republic-designed high-speed thin airfoil. After approximately 30 hours of engine development tests and more than 100 hours of engineering and performance testing completed at the Army Air Force's test base at Muroc Lake, California, the Air Materiel Command has contracted with Republic for around 400 of these jet fighter aircraft. Just as the P-80 helped to point the way, so does this 600-mile-an-hour XP-84 contribute to key phases in the development of our future supersonic aircraft. The need of a method for delivering 57mm or 75mm howitzers by air was recognized by the General Staff as far back as the Blitzkrieg days early in World War II, and orders were issued at that time for related research and development by Air Technical Service Command. Since aircraft suitable for this work had not yet been developed, it wasn't until the advent of the C-82 and C-97 that the Personal Equipment Laboratory at Wright Field was able to reactivate this long-shelved project. In August 1946, after a series of flight tests, it was concluded that the C-82 could be safely flown with the large cargo doors removed. With but minor modifications of this aircraft, development of the project advanced rapidly. With its simply constructed crash padding and platformer skid, the 75mm howitzer is easily loaded into the cargo compartment by standard Air Force's equipment. Loading into position is made easy by the conveyor rollers in the floor of the cargo compartment, which function as a conveyor during the extraction of the cargo. A 16-foot ribbon parachute attached to a nylon dragline having a tensile strength of 9,000 pounds extracts the cargo in a fraction of a second. The extracting parachute, in addition to decreasing the opening shock from the 90-foot cargo chute, also acts as a stabilizer, reducing oscillation to a minimum. Some of the research made possible by this method is the dropping of other pieces of equipment weighing up to 10,000 pounds at increased speeds, of course. For 75mm howitzers, this aerial delivery is easily handled and requires no major modifications of the C-82. The big chute eases its 1-ton load to the ground without tumbling and at the rate of 18 feet per second. A 4-point landing. This method chalks up another first in air transportation developments for Air Materiel Command. During the closing days of the war, our pilots over Germany were surprised by an occasional, extremely fast rocket fighter. After the Nazis threw in the towel, the Allies captured several of these rocket-driven planes intact and identified them as of the ME-163 series. These German films of their performance tests were found, leaving little doubt in the minds of our aeronautical engineers and designers, just how far in advance the Germans were of our own research and development on this particular type of aircraft. German data on performance of this first rocket fighter ever to be used in combat proved the feasibility of using rocket propulsion in airplanes. The speed and rate of climb with which a rocket-driven interceptor can meet an enemy squadron is illustrated by this German graph. Built principally of wood and duraluminum, the plane was designed for high-velocity performance. To eliminate possibilities of flutter, the elevators were mounted on the trailing edge of the wing, leaving only the rudder in the tail section. Power is provided by a Walter rocket engine. Weighing only 387 pounds, this unit has a maximum thrust power on the ground of approximately 3,300 pounds. Of simple design and with very few moving parts, it has been determined that this engine is easy to manufacture and needs comparatively little maintenance. An invaluable feature of jet and rocket engines that makes them ideal for interceptors is their ability to develop full power immediately after starting. The ME-163 rocket engine obtains power from the burning action that occurs when a fuel is brought into contact with an oxidizer. The fuel in this instance is a mixture composed principally of methyl alcohol and hydrazine hydrate, and the oxidizer is hydrogen peroxide. Both of these liquids are volatile, and it is their highly combustible nature that makes operation of the ME-163 dangerous. Wheels are attached to the plane for takeoff purposes only. After the plane gets into the air, the wheels are dropped. For landing, a retractable skid is extended from the bottom of the fuselage by pressure from a tank of compressed oxygen. Piloting is done from a conventional type cockpit. Oddly enough, this German test pilot is now cooperating with research engineers in the engineering laboratories at Wright Field. Although flight in the ME-163 was admittedly dangerous, no special provisions were made for pilot ejection in this series. The rocket unit contains a single-stage turbine that is run by steam, which is generated by passing the alcohol fuel mixture over crystals of potassium or sodium manganate. The turbine, in turn, runs two pumps that deliver the liquids to the combustion chamber, and the aircraft is immediately ready for takeoff. A speed of approximately 200 miles per hour is necessary for the plane to get off the ground due to the small wing area. After the wheels are released, a speed of 430 miles per hour is maintained for the best climbing performance. With that speed, the plane climbs to an altitude of about 22,000 feet in about 2.5 minutes, and to reach 40,000 feet takes only a total of 3.5 minutes. In these German tests, maximum speed for the ME-163 at 26,000 feet was about 560 miles an hour, and a little over 600 miles at 40,000 feet. Operating at full throttle, the plane is capable of flying for 6 to 9 minutes, but it can stay aloft for over 25 minutes by using a combination of power flying and gliding. Landing speed for this airplane is approximately 180 miles per hour, and an oleo strut mounted on the skid helps to absorb the impact of landing. Influenced by the design and performance of this aircraft, research and development on similar types of interceptors are now being conducted at our Muroc test base in California. The Nazi claim that Germany had rockets which could bombard the United States was not far removed from actual achievement. Missiles capable of ranges up to 3,000 miles were in the design stage when Allied troops moved into Germany. The Vergeltungswaffe 2, or retaliation rocket, commonly known as the V-2, had more than 12,000 persons engaged in the project in Germany, including 1,500 scientists, engineers and technicians, and 8,000 special workers. Many technical difficulties peculiar to the field of ballistics and aerodynamics were encountered in the early stages of V-2 development, but in designing, producing, and using it, the Germans proved themselves to be well in advance of any other nation. No discussion on guided missiles can fail to note the economic aspects of this type of warfare, and points emphatically to the nature of the next aerial conflict. A large number of V-2 rockets, complete and unassembled, were recovered by the Allies at the close of the war, and a goodly percentage of these were brought to our own research centers. These were rebuilt and modified at White Sands, where weather conditions for scientific research are ideal, and where rocket launchings for meteorological and engineering observations are now being obtained and analyzed. With the speed of this rocket, the nearest approach to the speed of a meteor, and its vertical range invading the spaces where northern lights waver and play their celestial game of tag, our research with data recording instruments and cameras will contribute much toward future developments deemed possible for mankind's penetration of the ionosphere. At the White Sands Proving Grounds in New Mexico, operated by the United States Army Ordnance Department in cooperation with the Army Air Force, the Navy, and many of our foremost technical institutions, the V-2 in recent tests has reached an altitude of well over 100 miles. The purpose of these modifications and tests at White Sands is to determine range, control, and relative data on this 12-ton guided missile. The engineering division laboratories at Wright Field are playing an important part in this research. Recently, their equipment laboratory developed a container installed with instruments and to be ejected from the warhead of a V-2 at the peak altitude and safely lowered to the ground by means of parachutes. In one end of the container, 2 parachutes are packed. First, an 18-foot ribbon cargo chute enclosed in a sleeve, then a partition to which is fastened a small brake chute. This partition, when locked, is released by a timer 165 seconds after the smaller chute opens. The small chute is 8 feet in diameter and also of ribbon design. In the pressurized compartment end of the container, a spring-wound tensiometer records parachute shock forces. Other data is procured, a potentiometer recording the shock forces in terms of electrical energy, a radar beacon to record potentiometer readings and track the trajectory of the container, and a movie camera powered by dry cells. The container, one half of which is packed with 2 chutes and a camera to photograph the functioning of the parachutes, and the other half a pressurized compartment housing data recording and signal instruments for tracking, is inserted in a tunnel in the warhead. An explosive charge in the tunnel's breech plate is set to eject the container 145 seconds after fuel shutoff. This rocket, already declared obsolete as a weapon, with our modifications, now provides a new vehicle with which our scientists can explore the unknown and affording our upper air meteorologists a feast of research. For placing the missile in its launching attitude, one of the original German Müller-Wagens is used. But for servicing the added research instruments and equipment at several stations in the body of the missile, Army Ordnance engineers developed the Gantry Tower, approximating the framework of a 5-story building on tracks. This device permits easy access for fueling, installation, adjustment, and checking of all control equipment and data recording instruments. Fuel in the German V-2 consists of calcium permanganate, hydrogen peroxide, alcohol, and liquid oxygen, 8 tons of it. This develops a maximum thrust of 68,000 pounds for 65 seconds, giving the rocket a maximum speed of 5,000 feet per second. With all servicing complete, the massive steel tower rolls back and the rocket is ready for firing. From inside the massive concrete blockhouse, test engineers count off the seconds before the big lift. Radio controls and radar tracking devices function clearly, and the flight of the missile is charted. Almost straight up into the ionosphere at a speed of 3,500 miles per hour. Then 145 seconds after fuel shutoff, the container is launched from the warhead. The movie camera in the parachute end of the container records the functioning of first the small brake chute. And 165 seconds later, the cargo chute. The container is safely lowered and recovered. By contrast, note the condition of not only the warhead after it was recovered, but the tangled mess that once was control devices of the rocket. Upon inspection, the container sustained only minor damage. The parachute, none at all. The data recording and tracking instruments are found intact.